I want to begin by telling you something the title of this piece won't tell you plainly, because I think intellectual honesty matters more than a dramatic hook, even in a story I find genuinely exciting. Nobody at CERN has discovered a new dimension, not confirmed it, not observed it directly, not proven anything close to it exists. What they have found is something more modest, and in its own way, more interesting than the more sensational framing suggests, a persistent, statistically significant anomaly in how certain particles decay, one that doesn't match what our best current theory predicts. And one of several theoretical explanations for that anomaly happens to involve the possibility of extraspatial dimensions beyond the three we experience directly. I want to walk you through what was actually found, why extra dimensions are even on the table as a serious hypothesis, and why physicists are being deliberately cautious about calling this anything more than a hint. To understand why this particular anomaly matters, you first need to understand what it's measured against. A theoretical framework called the Standard Model of Particle Physics, the most successful, most rigorously tested theory in the history of experimental science. I never lived to see the Standard Model reach its final, complete form. Most of its key pieces were assembled in the decades after my death, through the 1960s and 70s, building on quantum field theory that was itself still being actively developed during my own working years. But I understood, even in my own time, the deep ambition underlying this kind of work, the search for a single mathematical framework capable of describing every known fundamental particle and every known force, except gravity, all within one coherent, internally consistent theory. The Standard Model succeeded at this ambition to a degree that would have astonished physicists of my generation. It correctly predicts the existence and precise properties of quarks, leptons, and the force-carrying particles that mediate the electromagnetic, weak and strong nuclear forces. Its most celebrated recent triumph, the discovery of the Higgs boson at CERN's Large Hadron Collider in 2012, confirmed the final missing piece of the theory, the particle responsible for explaining why other particles have mass at all, a discovery that came decades after the Higgs mechanism was first proposed theoretically, and that validated the Standard Model's predictions with extraordinary precision. But physicists have understood for a long time now that the Standard Model, despite its remarkable success, is almost certainly incomplete. It doesn't incorporate gravity at all, leaving general relativity as an entirely separate framework that has never been successfully unified with quantum field theory, the exact problem I discussed in an earlier conversation about black hole singularities. It offers no explanation for dark matter or dark energy, the two components that, according to cosmological measurements, together make up the overwhelming majority of the universe's total mass and energy content, while the ordinary matter of the Standard Model actually accounts for only a small fraction. And it contains a number of parameters, the specific masses of fundamental particles, the strengths of various forces, that the theory simply takes as given, measured experimentally rather than derived from any deeper principle, leaving many physicists suspecting that some more fundamental theory must exist underneath the Standard Model, one that would explain why these particular values occur rather than some other set entirely. Because of this widely shared suspicion that the Standard Model can't be the final word, particle physicists have spent decades searching for what they call new physics. Any experimental result that deviates from the Standard Model's predictions in a way that can't be explained by measurement error or statistical fluctuation, and that would therefore point towards some deeper theory waiting to be discovered. This is where the recent CERN findings become genuinely significant, because they represent one of the more persistent and statistically compelling hints of exactly this kind of deviation that particle physics has produced in years. The specific measurement involves what physicists call B-meson decays, B-mesons being a class of composite particle containing a bottom quark, one of the 6 types of quarks the Standard Model describes. Paired with another quark to form a bound state, these particles are inherently unstable, decaying into other lighter particles within tiny fractions of a second after they're produced in high-energy collisions. But precisely how they decay, which combinations of lighter particles they're most likely to transform into, and with what relative frequencies, is something the Standard Model predicts with real precision, based on the underlying physics of the weak nuclear force, the interaction responsible for this kind of particle transformation. One specific category of decay that researchers at CERN's LHCb experiment have studied intensively involves what are sometimes called rare decays, or in some contexts, penguin decays. Originally applied somewhat informally by physicists working on the theory decades ago, referring to a particular pattern in the Feynman diagrams used to visualize these processes, diagrams that if you squint, some physicist apparently thought resembled a penguin. These particular decay pathways are rare within the Standard Model's predictions, occurring only through processes that involve what physicists call loop diagrams, where the decay proceeds indirectly through virtual intermediate particles that briefly appear and disappear according to the rules of quantum mechanics, rather than through a simple direct transformation. Because these rare decay pathways proceed through these indirect loop processes, they're particularly sensitive to the possible existence of new, undiscovered particles or forces. If some additional particle exists, one not accounted for in the Standard Model, it could, in principle, participate in these virtual loop processes alongside the known particles, subtly shifting the predicted rate or pattern of the decay away from what the Standard Model alone would predict, even if that new particle is far too massive or far too weakly interacting to be produced and directly detected in the collider itself. The specific measurement that has generated the most recent attention involves a decay process written in the notation particle physicists use as B0 to K star 0 mu plus mu minus, a B meson decaying into a particle called a K star meson, along with a pair of muons, the heavier cousins of the ordinary electron. Researchers analyzing data collected by the LHCb experiment using proton-proton collisions gathered over multiple years of the LHC's operation found that the actual observed pattern of this decay, specifically certain angular distributions describing the directions the resulting particles fly off in relative to each other, doesn't match the Standard Model's prediction as precisely as it should. If the Standard Model were the complete and correct description of the underlying physics, I want to be careful about conveying the actual statistical significance of this finding accurately, because precision matters enormously in how seriously a result like this should be taken. And sensationalized reporting on particle physics results has a long history of overstating preliminary anomalies that later resolve into statistical noise once more data accumulates. Physicists measure the significance of a potential discovery using a unit called standard deviations, often written using the Greek letter sigma. A result at 3 sigma is considered suggestive, worth further investigation, but well short of the threshold particle physicists require before declaring an actual discovery. A result at 5 sigma, corresponding to roughly a 1 in 3.5 million chance of the observed deviation being a random statistical fluctuation rather than a real physical effect, is the traditional threshold a field requires before a result is considered a confirmed discovery, the same threshold that was met before the Higgs boson's existence was formally announced in 2012. The BE meson decay anomalies, as they currently stand, based on the most recent comprehensive analysis published in December 2025, sit in a range that particle physicists describe as persistent and intriguing, but not yet conclusive, generally reported in the range of a few standard deviations, enough to justify serious ongoing investigation and refined analysis, but not yet enough to declare a confirmed break from the standard model. This has, in fact, been the pattern with this particular family of anomalies for close to a decade now. Earlier versions of this measurement, using smaller datasets collected earlier in the LHC's operational history, showed similar deviations. As more data accumulated and the analysis techniques were refined, some of the tension has decreased in certain related measurements while persisting, and in some specific measurements even sharpening in others. This is exactly the kind of situation that makes particle physicists simultaneously excited and appropriately cautious. A genuine, non-trivial anomaly that has survived years of increasingly careful scrutiny without either resolving into full statistical insignificance or crossing the threshold into a confirmed discovery. Now I want to address directly why extra dimensions specifically enter this conversation, because I think this is where the discussion tends to leap ahead of what the actual physics justifies, in ways that make for compelling headlines, but that deserve more careful unpacking. If these B meson decay anomalies do turn out to reflect genuine new physics, rather than an eventually resolved statistical fluctuation or an unaccounted for systematic effect in the experimental analysis, there are several distinct categories of theoretical explanation that physicists have proposed, and extra dimensions represent only one branch among several serious possibilities. Some theorists have proposed the anomaly could be explained by a new, undiscovered force-carrying particle, sometimes called a Z-prime boson, a heavier cousin of the known force carriers that could participate in the relevant loop processes without having yet been directly produced and detected in collisions. Others have proposed a class of hypothetical particles called leptoquarks, which would carry properties of both quarks and leptons simultaneously, something no particle in the confirmed standard model does, and which could similarly influence these specific rare decay processes through loop effects. Still others have proposed explanations rooted in supersymmetry, a broader theoretical framework proposing that every known particle has a heavier, currently undiscovered partner particle, a framework that was for decades considered one of the leading candidates for physics beyond the standard model, though direct searches for supersymmetric particles at the LHC have, so far, come back empty-handed across an increasingly wide range of possible masses. The extra-dimensional explanation belongs to yet another distinct theoretical family, generally building on ideas first proposed seriously in the late 1990s by physicists including Lisa Randall and Raman Sundaram, among others, proposing that our universe might contain additional spatial dimensions beyond the three we directly perceive, dimensions that are either compactified, curled up at a scale far too small for us to directly perceive or move through an ordinary experience, or that gravity, specifically unlike the other fundamental forces, might be able to propagate into these extra dimensions in ways that would help explain why gravity is so dramatically weaker than the other fundamental forces. A long-standing puzzle in physics, sometimes called the hierarchy problem. In some of these extra-dimensional theoretical frameworks, particles or force effects propagating through these additional dimensions could, in principle, produce exactly the kind of subtle deviations from standard model predictions that the B-meson anomalies represent, through mechanisms involving what theorists call Kaluza-Klein excitations, essentially higher energy versions of known particles that arise specifically because of the existence of these extra compactified dimensions. I want to be honest that this is a genuinely elegant piece of theoretical physics, connecting a specific, real experimental anomaly to a specific, mathematically rigorous theoretical framework involving extra dimensions. But I also want to be equally honest that it remains one hypothesis among several serious competitors, none of which has yet achieved anything like a confirmed decisive advantage over the others, based on current data. The honest scientific position at this stage is that we have a genuine anomaly worth taking seriously, and a menu of theoretical frameworks, new force carriers, leptoquarks, supersymmetric particles, extra dimensions, and others, any of which could, in principle, explain it, with the actual data not yet sufficiently precise to definitively favor one explanation over the others. I find myself thinking about this situation in relation to my own experience with genuinely uncertain, actively contested physics, and I think there's a useful comparison to draw, while being careful not to overstate the parallel. When Snyder and I worked through the mathematics of gravitational collapse in 1939, we had a specific, well-defined theoretical framework. General relativity leading us toward a conclusion, the existence of what we'd now call black holes. That seems strange enough that most of our contemporaries treated it as a mathematical curiosity rather than a serious physical prediction. It took decades of subsequent observational work before that prediction moved from speculative theory to confirmed physical reality. The current situation with these particle physics anomalies is in some ways at an earlier and more uncertain stage than where black hole theory stood even in 1939, because in this case, we don't yet have a single, clearly favored theoretical framework analogous to what general relativity provided for gravitational collapse. We have an experimental anomaly, real and persistent, and a genuine scientific debate about which of several competing theoretical frameworks, if any, correctly explains it, a situation that historically in particle physics has sometimes resolved with additional data revealing the anomaly was a subtle, previously unaccounted for systematic effect, and other times resolved with the anomaly holding up and eventually pointing toward a genuine Nobel-worthy discovery. What makes the current moment particularly interesting from where I sit reflecting on this decades after my own death is the timing. As of the middle of 2026, the Large Hadron Collider has just entered a major multi-year shutdown period beginning in June to undergo a substantial upgrade, transforming it into what's called the High-Luminosity LHC, a machine designed to produce dramatically more collision data than the current configuration allows, with new superconducting magnets and advanced computational systems designed to capture and analyze up to 100 times more collision events than the current setup permits. This upgrade won't become operational again until roughly 2030, meaning the specific B-meson anomalies I've described will need to wait years for the kind of dramatically expanded dataset that could potentially resolve with far greater statistical confidence, whether they represent a genuine crack in the standard model or an eventual statistical resolution back toward the theory's original predictions. I think this waiting period is worth sitting with, honestly, rather than glossing over in favor of more dramatic, immediate-sounding claims about dimensions being revealed, real experimental particle physics. At the frontier of genuinely uncertain questions often proceeds exactly this, slowly. Years of data collection, careful statistical analysis, competing theoretical proposals, and long stretches of genuine uncertainty before a question resolves clearly in one direction or another. This is not a failure of the field or a sign that physicists don't know what they're doing. It's simply the honest pace at which genuinely difficult, genuinely new physics gets established, when the effects being searched for are subtle enough that only enormous amounts of carefully collected data can distinguish a real signal from an eventually vanishing statistical fluctuation. I want to close by returning to the question the title poses directly, because I think the most honest answer captures something true about how frontier physics actually operates in a way that a simpler yes or no wouldn't. CERN has not revealed a new dimension, accidentally or otherwise. What CERN's physicists have found, through years of extraordinarily careful measurement, is a persistent anomaly in how certain particles decay, a real, statistically meaningful deviation from the predictions of our best current theory, one that has survived years of increasingly rigorous scrutiny without fully resolving in either direction. Extra dimensions represent one serious, mathematically rigorous theoretical framework that could, if the anomaly holds up and sharpens with future data, help explain what's being observed. But so could several other equally serious theoretical proposals, and the honest scientific position as of now is that we don't yet know which explanation, if any, is correct. What I find genuinely exciting about this situation isn't the specific possibility of extra dimensions, appealing as that idea is. It's the fact that the standard model, this extraordinarily successful theoretical framework that took decades to fully assemble after my own death, may finally be showing the kind of genuine, persistent cracks that physicists have been searching for since the theory reached its complete form. Every major advance in the history of physics I ever studied or contributed to has come from exactly this kind of situation. A well-established theory, successful across an enormous range of phenomena, running into a specific, careful measurement it can't quite explain, forcing physicists to ask whether some deeper layer of reality remains to be uncovered. Whether the answer this time turns out to involve extra dimensions, new particles, or some other framework entirely, the anomaly itself represents exactly the kind of genuine, hard-won uncertainty that has always, eventually, led physics somewhere new.